In the following lecture, I'm going to discuss Kw, which is known as the water constant. Now, Kw revolves around the dissociation of water. Remember that H2O, if you have a liquid water in liquid state, let's assume you have a container full of water, then these water molecules are going to bump into each other, and some of the water molecules are going to break down and they're going to produce two ions. One is H plus 1 and the other one is OH minus 1 ion. These ions would be in aqueous state because they would be dissolved in the same water. So you're already familiar with this. Water dissociates. Liquid water molecules are going to bump into each other and they're going to break down and they're going to produce H plus 1 and OH minus 1 ions, which are going to be in aqueous state. But remember, this happens very, very weakly. Water dissociates or breaks down or ionizes very, very weakly, or it ionizes very less. I am also going to try to descriptively show you how water ionizes. So here are my two water molecules. Water has an oxygen atom which is bonded to two hydrogen atoms, and oxygen has 4 unused electrons in the outer shell. These are your two lone pairs. There's another water molecule. Remember this, that water is a highly polar molecule. It's capable of forming hydrogen bonds because oxygen over here is extremely electronegative. It's one of the most electronegative elements. This oxygen over here is also very, very electronegative. So what oxygen would do is that the electrons that are being shared in this bond, they would be pulled closer or would be attracted closer to oxygen. So the hydrogens, those electrons, the shared electrons would be away from hydrogen. So the hydrogens will have a partial positive charge or a slight positive charge. And the oxygen atom over here would have a partial negative charge, and that partial negative charge would be larger because there are lone pairs as well. So these lone pairs, their negative charge would also add up. So this negative charge would be very, very strong. So these shared electrons would be lying closer to oxygen. So it's going to be a highly polar molecule. So the same thing applies to the other water molecule. The hydrogen would have a partial positive charge. This hydrogen would also have a partial positive charge, and the oxygen atom would exhibit a partial negative charge. Now, because of this polarity, the two water molecules will be attracting each other very strongly, and the force of attraction that would be present would be called hydrogen bonds, which is this partial positive hydrogen would be very strongly attracted to the negative charge on these lone pairs. So the two water molecules would be strongly attracting each other. The lone pairs on one oxygen would be attracted to the positive hydrogen on the other water molecule. So these are your hydrogen bonds. The line that I've drawn in orange, these are the intermolecular forces or the strong attractive forces between one water molecule and the other water molecule. Now, when these water molecules, and remember we're talking about liquid water molecules. Liquid molecules are energetic, so they can overcome these attractive forces. So these water molecules are bumping into each other and they are sliding past each other, but the attractive forces are there. This positive hydrogen is going to be attracted to the lone pairs on the other water molecule. Sometimes what happens is that the force of attraction, the positive hydrogen would be attracted so strongly to this lone pair that this bond over here, this oxygen hydrogen bond would break. The reason why it would break is because there are two shared electrons in this particular bond. But remember, these lone pairs have a negative charge. So if this negative charge comes sufficiently close to this hydrogen, the electrons over here are going to be repelled by the negative charge on this other water molecule. So these electrons are going to be repelled further away. The positive hydrogen will be attracted even closer, and eventually what would happen is that this bond over here is going to break apart. The lone pairs in the shared electrons are going to be repelled by the negative charge over here, so they get pushed to the other side. The positive hydrogen is attracted by these lone pairs. So this bond over here eventually splits. Lone pair is going to the other side, the positive hydrogen getting attracted to this water molecule over here. So the products that are going to be formed are going to be this. The hydrogen that was over here, this hydrogen over here is going to be attracted and pulled. So this H plus 1, it would now be plus 1 because it has lost its electron because those electrons were being repelled by the lone pairs over here. So the H plus 1 then goes and forms a dative bond. It gets attracted to these lone pairs, ends up forming a dative bond, and a molecule of H3O plus 1 ion is formed, which is hydronium ion. And this other side, the bond broke. This bond over here broke. The electrons over here got repelled by the lone pairs over here. So these electrons got pushed to the other side. So if they get pushed to the other side, remember hydrogen lost its electron as well. That electron got added to this ion over here, and this would be your OH ion. So these two ions would be produced when two water molecules collide. The hydrogen from one water molecule, this bond over here breaks, gets attracted to the lone pairs on the other water molecule, and ends up forming an H3O plus ion, and the other ion that is formed is an OH minus 1 ion. So I've shown you an exact representation of what's happening when two water molecules collide. So the actual reaction would be something like this, that there are two water molecules, H2O bumping into another H2O molecule, and they end up forming H3O plus and OH minus 1. So this would be your actual equation. We usually simplify this above reaction by using this reaction, which is that H2O dissociates, producing H plus 1 ions and OH minus 1 ions. These H plus 1 ions basically are the ones that end up combining with water molecules to form H3O plus ions. They form a dative bond with water molecules and form H3O plus 1 ions. So in your actual solution, H plus 1 ions are not floating around. It's basically H3O plus 1 ions that are floating around. So this is an approximation. So you're always going to, in a lot of places, you're always going to notice this equation written, where water dissociates, producing H plus 1 ions and OH minus 1 ions. But in reality, it's two water molecules combining and reacting with each other, producing, one loses H plus 1 ions, ends up forming OH ions, and the other one ends up gaining H plus 1 ions, forming an H3O plus 1 ion. And this H3O plus 1 ion, remember, is in reality the H plus 1 ions that we are always talking about. Now this over here is the reaction that I'm going to take forward. The water dissociating into H plus 1 and OH ions ionizing. Remember, pure water ionizes very weakly. The concentration of H plus 1 ions, or we can call them H3O plus ions, is very, very less. It's 1 into 10 raised to minus 7 mole per decimeter cube. So it's almost very close to zero. So, and remember that if water dissociates, breaks down, ionizes, produces one H plus 1 ion, then it's going to also produce an equal amount of OH ion. So if H plus 1 ion concentration is 1 into 10 raised to minus 7 mole per decimeter cube under standard temperature and pressure, OH ion's concentration is also going to be exactly the same. It's going to be 1 into 10 raised to minus 7 mole per decimeter cube. So they're both going to be in equal concentration if water dissociates, ionizes, and the concentration is very less. And remember, this concentration of water of ions H plus 1 and OH minus 1 is under standard conditions, which is that 1 atmosphere is the pressure, 25 degrees centigrade or 98 kelvins would be the pressure. So under these conditions, standard temperature and pressure, that would be the concentration of H plus 1 and OH ions at room temperature. Now let me highlight this reaction, and I'm going to focus on this equilibrium over here. Remember, it's an equilibrium reaction. Whenever there's an equilibrium reaction, there's going to be an equilibrium constant, which is the ratio of the concentration of products to the ratio divided by the ratio of the concentration of reactants. Over here, my products are H plus 1 and OH minus 1. So it's going to be the concentration of H plus 1 into the concentration of OH minus 1. And I'm going to divide that by the concentration of my reactant, which in this case is water, H2O. So I'm going to divide that by the concentration of H2O. Now, one thing that I would highlight is that H2O liquid, if you can imagine a container having water, water ionizes very, very weakly. There's hardly any H plus 1 ions. It's 1 into 10 to the minus 7 mole per decimeter cube. OH ions is also, there's a negligible amount of OH ions present. The quantity of OH ions is very less. So if you have pure water, then water would be it's going to be in large excess. So so if you have a container full of water, then it's mostly H2O liquid. There is hardly very little dissociation actually happening. So H2O liquid is in large excess. And whenever a reactant or a product is in large excess, its concentration almost becomes constant. So the concentration would hardly vary. Hardly changes, or you can call it's almost constant. Constant. And let me show you in detail why, if some reactant is in large excess, its concentration almost becomes constant and irrespective of where the equilibrium is shifting. So for example, I just told you that water dissociates very, very little. So if I have 1 million, let's say 1 million is 1 followed by 60 molecules of H2O liquid, and in the same solution very little water dissociates. So let's say I have 5 ions of H plus 1 ions being produced and 5 ions of OH ions being produced in the same solution. So water dissociates very, very less. So a container full of water would hardly produce any H plus 1 or OH ions. So the quantity of the products that are being formed is very, very little, and the quantity of water is it's in large excess, which means that there's a lot of water molecules. Now let's say the equilibrium shifts to the left, which means it goes backward, and it strongly shifts to the left. Let's say 80% of the products get converted into water. So if the equilibrium shifts to the left, 80% of the H plus 1 and OH ions, they get converted into water molecules. So you're left with just one H plus 1 at equilibrium and one OH ions at equilibrium. And what change would happen to the amount of water that's being produced? So 4 H plus 1 ions would combine with 4 OH ions, and they're going to produce water molecules. So 4 water molecules will be produced. So the amount of water at equilibrium, if the equilibrium shifts, is going to become 1,000,004. So the quantity or the concentration of H plus 1 changes drastically. It decreases by almost 5 times. The quantity of OH ions also decreases by 5 times. But if a few molecules of water are produced or more produced, or if the equilibrium shifts to the left, the quantity of water or the concentration of water hardly changes. So if some reactant is in large excess, then its amount hardly changes. Percentage wise, it hardly changes. So it's almost, the concentration of water almost remains constant. So only those concentrations vary that have a smaller concentration. That changes drastically. The reactant that is in large excess, its concentration would hardly vary if the equilibrium shifts to the left or whether it shifts to the right. So coming back to my expression for Kc that I had written for this equilibrium, I've already told you that water doesn't ionize it ionizes very less. So there's water is in large excess. There's a large quantity of water present. So its concentration is almost constant. So if you look at the expression over here, this water over here, its concentration. So its concentration is constant, or it hardly varies, or the concentration change in the concentration of water is negligible. So there's no point in writing a reactant whose concentration is not changing at all. So I'm going to, since this is a constant, I'm going to combine the two constants together. Kc is also a constant, so let's put the two constants together and rearrange and write this again. So this over here is the expression that I'm going to get. It's Kc multiplied by the other constant, which is the concentration of water. I've combined the two constants together, and that would be equal to the concentration of H plus 1 and the concentration of OH minus 1. They would be multiplying together. And since both of these are constants, I'm going to name another constant, replace them with another constant, which is called Kw. So this is your Kw. It's called the water constant, which is equal to the concentration of H plus 1 into the concentration of OH minus 1. So this over here is my Kw. Now, I've highlighted the expression as well. Now, I'm going to try and calculate the value of Kw, which is the concentration of H plus 1 and the concentration of OH minus 1. It's the product of the two concentrations. And we know that at room temperature, standard temperature and pressure 1 atm and 25 degrees centigrade, water ionizes and produces H plus 1 ions. So the quantity is 1 into 10 to the minus 7 mole per dm cube, and OH ions, and the concentration is 1 into 10 to the minus 7 mole per decimeter cube as well. So what I'm going to do is I'm now going to try and calculate the value of Kw, which is going to be, it's going to be the product of the two. So it's going to be 1 into 10 to the minus 7 mole per decimeter cube multiplied by 1 into 10 to the minus 7 mole per decimeter cube. So it's basically getting squared mole per decimeter cubed. And the answer that I'm going to get is going to be 1 into 10 raised to the power minus 14 mole squared. Focus on the unit as well. So this would be the unit for Kw. It's going to be mole squared dm minus 6, because the two units concentration is being multiplied by concentration. So the unit would multiply as well. It's going to get squared as well. So this is your value of Kw. And so I'm going to write down the value of Kw over here. It's going to be 1 times 10 to the power minus 14. And the unit is going to be, it's going to be mole squared and dm minus 6. So we also have a value of Kw. But this value of Kw is only true under standard conditions at 25 degrees centigrade and 1 atm pressure. If you change temperature, temperature is the only thing where equilibrium constants and their value changes. So if you change temperature, the value of equilibrium constant Kw would also change. So I've written this down, that value of all equilibrium constant, they change with temperature. So as long as you're not changing temperature, the equilibrium constant Kw is going to remain 1 into 10 to the minus 14. But what happens if you increase temperature? Remember, Kw increases at higher temperatures, which basically means if you increase temperature, the equilibrium, which we had written down earlier, this equilibrium over here at the start, if you increase temperature, dissociation would be higher. It would become easier for water to get ionized, for water to break its bonds and form H plus 1 and OH ions. So at higher temperatures, there are going to be more products. If you have more products, then the concentration of H plus 1 and OH ions is going to be higher, and the value of equilibrium constant is also going to be greater. So remember this fact that Kw increases at higher temperatures. As you increase temperature, more ionization would occur and more H plus 1 and OH ions are going to be produced. So you're going to get a higher value. Otherwise, if you don't increase temperature, you do any other changes, increase pressure, decrease pressure, or change concentrations, the value of equilibrium constant is going to remain exactly the same.